Well, hello. Welcome to I think this is our 13th, maybe 14th eVTOL Writers Group interview. I might be off a little bit on the count. There's a few that have happened that we were kind of short runway to take care of, but this will be an excellent one, just as all the other ones have been. Today we are featuring leadership from EP Systems to come in and talk about their their newest battery technology, the EPIC system. And we also have our star moderator for today too, Mr. Graham Warwick. Mr. Warwick, or should I say just Graham, is the executive editor for technology at Aviation Week and Space Technology, and is a contributor to Aviation Week's new Advanced Air Mobility Report publication. So with that, I'll let Graham go ahead, say a couple words, and we'll turn it over to the EP folks to do their presentation. So with that, Graham, I'll give it to you.
Thanks, Jim. And again, welcome everyone to this VFS eVTOL Writers Group presentation from Electric Power Systems. EP Systems has taken an early lead in the development of safe and certifiable battery packs for electric propulsion, which is probably the key technology enabling this revolution we are seeing in air mobility, whether it is eVTOL, eSTOL, or eCTOL. So joining us today from EP Systems are Nathan Millecam, co-founder and chief executive officer. Before founding EP Systems, Nathan served as program manager of the Honeywell 787 flight control electronics power system, which included lithium-ion batteries. He then went on to become the product manager for Honeywell's electric power systems portfolio from generation to distribution before founding EP. He today is joined by Randy Dunn, co-founder and chief science officer at EP Systems. Randy began his career at McDonnell Douglas, now Boeing, working on the C-17 program in avionics test. He later joined Maxis Tech, where he worked on the International Space Station program. And in 1998, Randy founded Phillips Aerospace, which continues to support the military and commercial satellite industry. And rounding out the EP Systems team today is Michael Armstrong, chief technology officer. Before joining EP Systems, Mike was the hybrid propulsion lead at Rolls-Royce Liberty Works. But in his 3 years at EP Systems, he has worked on more than 20 clean sheet battery and electric propulsion system designs for aircraft, 7 of which have progressed to flight. A lot faster than he probably saw things move at Rolls-Royce. So gentlemen, over to you.
All right, well, let me first start off by thanking Jim for having us, and then Graham for moderating. Very much looking forward to the conversation here today. As far as what I'll cover this morning is I'll just talk very briefly about who we are and a little bit of a bio on our company. We're a mission-driven company and driven by, I think, a similar vision that us and a lot of our colleagues see going on in aviation right now, and talk a little bit about that vision. The other thing that I'll highlight is it's challenging to do batteries. I think, Graham, you hit the nail on the head where you said it could be the pacing technology. We certainly feel that opportunity as well as that pressure to advance technology as fast and as far as we can to enable what's really emerging as a very, very exciting time in aviation's history. And so EPIC is what we see as the very first piece of advancing aviation into an electrification and hybrid electric propulsion space. So maybe if we can advance to the next slide, let me just talk a little bit about who Electric Power Systems is and what we do and what our products are focused on. So we're very focused on the aerospace and defense arena. And we look at high power, we look at high voltage powertrains, and we specialize within the energy storage system complex. Within energy storage, there's a lot of things besides just batteries. There's a lot of power electronics, there's controls, there's power distribution, and those controls also happen to enable some of the key fast charging capabilities that will be needed to maintain a high utilization of these assets as they're put into service. Besides just working in aerospace and defense, we have done some things in automotive as well as in marine and industrial traction, and so we leverage a lot of those lessons learned from other markets to hopefully bring the best that we possibly can to this new advanced mobility space. As far as a history, we've been doing this for a while. Some of our core team, you'll hear our Chief Science Officer Randy Dunn. He's been doing this since the 90s. Mike Armstrong's been working on hybrid electric space before it was actually cool to talk about hybrid electric and all electric propulsion. But the core company was spun out of one of the largest semiconductor companies in the world. That happened in 2016. And since that time, we've done about 30 different unique aircraft designs for energy storage system. As Graham had stated, we've got 7 flying right now. We actually anticipate that that number will expand to 12 by the end of this fiscal year. We're located in North Logan, Utah. We started in Los Angeles. We still have a site in Los Angeles to do innovation. And right now our employee base is above 70, and it's continually growing and expanding. And you can see some of the highlights here of where our people have come from. Very, very proud of the team that we've assembled here and their background, not only in aviation, but in other industries that bring a lot of technical knowledge and contributions to our field. Why we're excited today is, as you can see in primary shareholders, Boeing and Safran made a large investment in us. In fact, it was the largest investment that those venture funds had made to date. And the mandate of that investment was to do just this, was to push energy storage and push electric powertrains forward as fast as we possibly can, but then have it appeal to a broad market. And so today's announcement really is the culmination of what we've been doing the last year and a half. I think we've been in a bit of stealth mode, and so we're excited to finally show people what we've been working on as a result of that investment. So let's go to the next slide. So this talks a little bit about what our mission and our vision and how this product fits into that mission and vision. And what we see is what many others see is really what we're terming to be a renaissance in aviation. And it's very exciting for those of us who have been in aviation our entire careers, where aviation now starts to feel like a startup space. Where there's high growth. And usually whenever that has happened in aviation, it has been preceded by a major step change in propulsion technology. And so some of the key things that propulsion technology, particularly in the electric space, has allowed us is to rethink how aviation can enable our transportation systems. As many of us know, transportation is something that's very strategic to all of the communities and the nations that we live in. It's how we get around, it's how goods get around, and a lot of our economic growth comes by how efficient our transportation systems are. And over the years, we've seen costs increase, we've seen congestion increase in these transportation systems, and an airborne asset that's powered by an electric distribution system really is a game changer. It's a game changer in a lot of areas where airborne missions can start to compete with ground-based missions. We can have a level of capacity in the sky that it's hard to compete on the ground because of the third dimension that we're taking advantage of here. It also allows us to distribute the propulsion across the aircraft. And when we can distribute it, we can dream up new concepts such as the popular electric vertical takeoff and landing vehicle that can do things like take off like a helicopter and then fly like a fixed wing. The propulsion systems that are being advanced has allowed the whole aviation conversation to start to really be changed of how it can serve just the broader community. And so we want to be at the forefront of that. We want to be able to enable and usher in this renaissance period. If you go to the next slide, that sounds great. We're all working towards this vision, but as many know, it's challenging. It's very, very challenging. And what we see is the challenges or the problems that need to be overcome to usher in this new renaissance period in aviation really focused around 4 key areas. The first one being safety and certification. Aviation is one of the safest ways to travel, and that's come through a lot of lessons learned. It comes through a very robust certification framework. Whenever we change technology, then typically it takes a while for the certification frameworks to catch up with that technology, as we've seen particularly in our space in lithium-ion batteries. When the first lithium-ion batteries were put into service in the mid-2000s, there was a lot of growing pains, and the cert framework that we had used found was not as robust as we'd like it to be. And primarily that's due to just the nature of batteries, particularly the advanced chemistries within the lithium-ion family, is they're prone to what we call thermal runaway, which is a really nice way of saying a fire or an explosion can happen. And when a fire and explosion can happen on an aircraft, that means potential hazard effects of either losing the aircraft itself or losing propulsion power, which can then lose to a catastrophic failure. And so we have to guard against those things in aviation that's not really required in other markets, such as automotive or industrial traction. The other challenge that we all face is cost. And cost is typically driven by this strong desire within aviation to customize whatever parts that we develop for these aircraft. And customization is usually required just to get the weight out, to get to an aircraft that can close technically and meet the mission requirements. And so when we often talk about battery design, we'll joke that it's like pushing on a balloon. When you try to optimize one area, such as cost, you may be causing the weight to go up, or you may be causing a degradation in safety. In order to make these advanced lithium-ion batteries happen, we can't do that. They have to be very, very safe. They have to be low cost. They have to be certifiable to aviation standards. And then the weight absolutely has to be benchmarked. The other challenge that we have that's tied to weight is batteries typically either want to be an energy solution or a power solution. And what we mean by that is energy is generally driven on a watt hours per kilogram, which is a figure of merit that's used to how much energy can we put just in 1 kilogram. Power is usually driven by, well, how fast can we utilize that energy? We may need a lot of power if we want to get into vertical flight, but once we're at cruise, not so much. So aviation batteries really have to be a good hybrid between power and energy, where cell technology doesn't want to do that. They either want to be a power cell or they want to be an energy cell. And again, we have to overcome both of those. The last one that's important and non-trivial is the infrastructure. And so when you start to look at the amount of capital that's required to just put in place things of not only charging assets, but potential assets that may be required to protect the grid from overload, or even protect the operator from too much cost being allocated on each kilowatt hour of energy as a result of the demand that's being asked for from the aircraft. These are big challenges that need to be addressed. And we have been working in this area, and hopefully in future meetings we can unveil some of the technology and some of the products to address infrastructure. But one of the things that we'll address today is the idea of fast charging. If you can fast charge an asset, you can turn it around pretty quick, and therefore you can utilize that asset. And the more you can utilize the asset, the more money that the operator makes and the less cost overall that asset has. So with that, I'll hand it over to Randy Dunn, our Chief Scientific Officer, to talk a little bit about how we've addressed these challenges.
So Nate, I'll jump in there with the challenges and looking at overcoming them. So you go to the next slide. As Nate said, safety is central to everything we do at EP Systems. And in the past, and then we look at our short history here, we've had the privilege of working with technologists at NASA, the FAA, and across the breadth of the aerospace industry to advance battery safety and the focus on this area of electrically powered flight. And this primarily, as Nate mentioned, focuses on the advancement of thermal runaway containment and being able to mitigate the consequences of that potentially catastrophic failure. In addition to that, we've looked at solutions that tries to mitigate cell-to-cell propagation that would lead to these larger events. So focusing on the point of protection at the battery cell level, at the module level, at the system level, and at the integration level, which enables battery safety. By advancing these technologies with these partners, we've been able to ensure our ability to be compliant with the current certification standards like DO311A, but it also has helped us to look to the future to see how these standards can be enhanced to increase the safety and the efficacy of these towards this really new application of electric aviation. As Nate mentioned, the main challenge with battery safety, or one of the main challenges with battery safety, is that it cannot come at the cost of weight. The battery system is a lot more than just cells and cell chemistry. When we design a battery system, we have to look at things like containment, controls, electrical connections, high voltage protection, structural integration, venting provisions for thermal runaway, cooling, and thermal management. And all of this has to be brought into the design of the battery system. And EP Systems has developed benchmark technologies which focus on reducing this packaging overhead and allowing us to get the lightest solution possible for these applications. In doing so, one key constraint, obviously, as Nate said, is cost. And that's not just the cost of the module, but that's really the cost of operations of the module. So EP Systems is laser focused on providing means to reduce the customer operating costs. So that includes the cost of the battery itself, and how easy is it to install into the aircraft, to be implemented in the aircraft, and then how long can you use it in operation? How long will it last? Will you have to replace the battery in 6 months, or will you have to replace the battery in a couple of years? So in order to meet these cost constraints, this focuses on not both battery design, but it also includes the application of advanced manufacturing techniques, as well as looking at what the product is. And so one of the key things that you'll see about the EPIC solution is that it's a modular approach to battery system integration. By taking this modular approach, it allows us to take advantage of economies of scale with a battery system that is able to be customized towards various air vehicles, but it also retains this common building block that's certified for various types of systems and maintain that core element. And as we talk about cost, it's really operating costs. So this reconfigurable and modular battery system allows for low cost operations by having high life, but also low cost sustainment by marrying the onboard solution with onboard sustainment and support systems. As Nate mentioned, we will be talking in the future, in the coming months, about some of these additional products that interface with this EPIC modular solution that helps minimize that cost. But one of those elements is allowing for the module to have a secondary life opportunity off-board of the system. And so this really frames the technologies that are implemented towards this EPIC solution. And I'm going to let Randy talk specifically about the solution itself and how it installs in the aircraft.
Thanks, Mike, Nate, appreciate it. So as they outlined, there's quite a few constraints on designing a battery system to comply with these numerous requirements for safety and cost and functionality. And so the culmination of that, I think we're one slide behind, or at least I am. Thank you. We're pleased to offer this EPIC battery line. It comes in a couple of different flavors, and the reason for that was expressed earlier. Batteries can be high energy, that's the watt hours per kilogram, or they can be high power, which is watts per kilogram. And we've worked with 20 plus programs over the last several years and seen quite a variety of applications, from micro hybrids to all electric, large, small, some starter and some special type applications as well. And in order to address the needs of all these markets with a common kind of core module design, architecture, we have implemented 3 different types of modules. So on the left there, you have the energy module. So it's focused on high energy, obviously, and a little bit lower power. But in aviation, we've realized that nothing is really low power. Everything seems to be fairly power intensive. So even though it's considered energy and high energy and not as powerful as the other ones, it's still capable of really high power. As you can see, there are 10C discharge rates. So in some folks' eyes, maybe they would see all of our batteries as high power. But there's different levels of that. And then in addition to the energy, we have the power module kind of in between the two to meet some hybrid electric applications, and then the ultra for APU start and military applications, but also kind of micro hybrid applications where you need to discharge a lot of power in a very short period of time. You need to be able to have a robustness to do that thousands of times so that there's an ROI and value of the battery and it's not being replaced every few weeks. So you can see the cycles and some of these power demands are quite a bit higher than in other industries such as automotive. But those are, what we found is that those are the kind of requirements necessary to meet this emerging electric aviation market. You can see that the modules, although they have different shapes, they're common in construction. And as opposed to maybe other battery systems, like maybe automotive, where you see modules put into a bigger case, these are basically designed to be used as is, meaning that the battery modules themselves are encased in a protective layer for the containment of the thermal runaway events. So they're complete with the electronics inside to manage the cells. They're complete with a liquid cooling mechanism support and ventilation of a thermal runaway event, and communications to the battery management system for voltage management, state of charge estimation, and so forth, temperature measurement. All those features are integrated into the modules. So the modules themselves are not a complete battery. They're intended to go be put together in series to create a high voltage string. These are meant to be kind of like Legos or building blocks going into a system that would be put together to create strings, and then multiple strings to complete an entire energy storage system. There are some additional supporting elements that go in there, but for the most part, these modules themselves are fully contained sub-batteries that can be linked together to form larger systems. Okay, the next slide, please. And this is kind of a visualization of that. You see in the top there, there's modules that are put in series with some battery management electronics on either side there for safety and communications to the aircraft, but they get stacked together in series. You'll see another configuration there just below that with where the batteries are stacked, and then there's a ventilation plenum on top of there to take thermal runaway and pipe that out of a common vent outside the aircraft. At the bottom's a different configuration yet, and then bottom to the right is a smaller battery for like APU, where there'd be a single battery that's only 28 volts to do starters. That's got integrated electronics built into it. So it just shows the variety of applications and configurations that we can achieve with this standard building block. And we believe that these 3 modules and these types cover quite a wide range of aircraft and needs for our customer base, including the emerging eVTOL market, retrofits. There's a number of aircraft flying with our batteries on them, and kind of a retrofit, electrification of existing aircraft to make them green and all electric and move forward. Also general new developments in fixed wing for thin haul and so forth. And then a traditional aircraft too, mostly for starters because they don't have a lot of batteries, but there's also hybridization of those aircraft as well. And that's where the epic power ultra power can come into play, where they can discharge short periods of time to act as a micro hybrid for larger aircraft. So the standard building block, it's a good offering to get complete battery systems put together quickly to support our customers who are usually kind of frantically trying to put together a battery system to achieve some sort of a goal and move their programs forward. And they can use our products knowing that they're currently in certification with the FAA and EASA right now, and we've already gone through the most critical DO311 safety tests for thermal containment as well as shock and vibration tests, the most critical ones. And now we're in the process of going through the formalities to get that certified by the FAA, so that we can, claim that compliance. And so customers have something they could use near term, and then knowing that it will be certified probably early next year. And so it gives them a path forward for their aircraft, so they can do test flights now, and then know that they'll have a partner down the road when they want to certify their aircraft in the next coming years. Okay, and I think I'll hand it off back to Mike for the next slide. Thank you.
Yeah, thanks, Randy. I want to give you kind of a little walk around of the technologies that support this EPIC module. As we talked about before, the module is really designed to eliminate some of the fundamental barriers of adopting energy storage in the aircraft, and easing the issues associated with integrating the battery into the air vehicle. And so the module was designed to be adapted to various space claims and orientations. And it includes turnkey provisions for venting and cooling, as you see there at the top of the module. There are interfaces for venting out ejecta, as is required by battery certification from the FAA, as well as provisions for integrating thermal fluid interaction with the module from other either onboard or offboard cooling systems. In addition, we focused on reducing other complexities associated with battery installation, specifically the reduction of complex comms wiring or power cable harnessing required to connect the modules together. They actually will, as you saw in the prior picture, they will essentially stack together with very minimal overhead in terms of harnessing, and that includes a reduction in the associated mass. It also has a mature data acquisition system with power management and communications that's being developed compliant to DO 179B, and it provides compliance to DO 311A containment. All of this is done with less than 20% total packaging overhead. And by packaging overhead, I mean for every, say, pound of battery, only 20% of that is associated with non-cell mass. And so this desire to, say, take advanced cells and introduce them into the aviation, you really need to do that with a very, very low overhead and packaging mass. As was mentioned by Nate, in order to support paced aircraft operations, the module has the ability to be charged at a 3C rate. And what that means is that it enables a 20-minute turnaround time of the vehicle. Now, the way we do that is done through both careful selection and design of the cell chemistry, but it also involves the provisions for this highly effective integrated liquid cooling system that can not only allow for fast charge, but also preconditioning the battery post-charge to enable this fast turnaround. We include high temperature composite case, which enables a low temperature sidewall of the module during, say, a potential thermal event, which minimizes some of the complexities associated with installation on aerostructures. And really this combination of technologies has resulted in a really industry enabling battery design, which is modular, scalable, and able to fit multiple different aircraft from fixed wing to eVTOL applications. So with that, I'll turn it back over to Nate.
Right, we can advance to the next slide. So this slide is really just to give a little bit of a shout out to some of the folks that we've had the privilege of working with, and then give a little bit of a preview of where we see this being deployed, and hit on another key point. And the key point is, in order to solve a number of these major complicated challenges, really it takes a village. It takes a number of people. It takes good academia, it takes good government, it takes good government agencies, it takes good just good firms working on this in industry. And so this is to highlight some of the public-private partnerships that we've been able to work with to mature the technology and that we intend to work with in the future. So there's definitely a shout out to NASA and giving us a chance to work on these exciting technologies and deploy these in some of their X-planes. But also looking at a state level, particularly with the state of Utah, who's been very forward-leaning in deploying electric aviation networks in multiple applications. And then also there's a major shout out to Boeing and Safran. We look forward to continue to work with a number of these agencies in not only battery technology, but now how we can deploy them into propulsion architectures, and then also then deploy them into different aircraft as well. And so as we move forward, as I stated, we anticipate that we'll be announcing many more partnerships and more application of this core module that we've announced today. But this summarizes the presentation for EPIC. So if we go to the next slide, we want to thank everybody. And I guess, Graham, we'll turn it back over to you to ask questions.
Thank you very much, gentlemen. Very interesting. So I'm going to go to which is a fascinating one. The first question, one of the questions that come in, said, so we're seeing a lot of the OEMs actually say that they're vertically integrated. They're doing the battery design in-house because they consider it. Well, they give two reasons. One is they say there was no supply chain, and secondly, they think it's core technology. How do you view that, and what do you need to do to be competitive if you have some of your potential biggest customers doing it themselves?
Yeah, that's a great question. So number one, we hope to solve the supply chain issue by giving a great supply chain option. Number two, I think you have to address that both through cost and through technology performance. And so usually why people will vertically integrate is they feel like they can get a gain both in those areas where they can take a kilogram or a couple kilograms of mass out here or there, or they feel that their aircraft volume warrants that they can get a cost advantage by leveraging their volumes. If you look at our strategy to essentially what we call go wide and to do something that modular that can work across multiple platforms, if you start to say, well, hey, maybe one eVTOL platform is a lot of volume, but what if you can leverage the volume of 6 eVTOL platforms? And what if you can also add on top of that volume fixed wing applications or military or APU starts? When you start to look at that level of volume, it significantly dwarfs what one platform can do. And so our contention to the marketplace is that kind of volume is going to make it a lot cheaper than just one platform. And as long as the technology is benchmarked into what it can do with energy and power and having the lowest operating cost, we believe that's a winning solution of the vertical. Great.
So can you, thanks for that, can you explain how you go about certification and also give us some insight into your timeline? Are we talking here about certifying the battery as part of the aircraft certification or as part of the propulsion system certification like Part 2033? Or are we talking here about like a TSO that you then pull into the aircraft or the propulsion system? How do you go about certifying?
Yeah, I think I'll let Mike answer that one. That's a great question.
Yeah, that is a really great question. The path to certification for the EPIC module and system is through TSO. So currently the framework for certification for battery, lithium-ion battery certification is TSO C179B, and there is an avenue through DO311A and associated other software and hardware provisions for certification of batteries under TSO. So that's the EPIC system. Now, obviously, post TSO, there is additional work, obviously, for installation. There are some installation effects. So we're very cognizant of and strategic about how we have executed that TSO certification plan to enable and minimize the effort associated with customers adopting that TSO and installing it in the vehicle. So obviously you can TSO a lot of different things. Doesn't mean it's going to actually be valuable, because you may have to go redo a lot of work for the installation. And so we've been very, very cognizant, based on all of the other installations we've done on the 20 or so different designs, 20 to 30, that we are not putting undue burden on the integrator for certification. So we're solving a lot of their integration issues through that TSO.
So am I correct in saying you're aiming for a TSO in 2022? Will you supply EPIC batteries in advance of that, folks, to begin integration?
Yes, so the EPIC system will be able to, I think we're already starting to work with some customers around plans for receipt of EPIC modules and EPIC systems late this year. So it will be obviously non-certified, but we'll have opportunities for installation and testing with the system prior to the certification.
Can you identify anybody who's going to use the module yet? Or?
I think that's forthcoming right now. We'll not at this point. There is high interest. It's not just one customer. There's a number of integrators that are looking at this and are planning their product around it.
So you say you worked on 20 to 30, propulsion system designs. How broad is EPIC in terms of meeting what you see as that demand? I mean, is EPIC designed to meet all 20 to 30 of those, or is it some subset of those 20 to 30 that you've looked at that EPIC can actually meet?
So that's a good question, and it's really the question of that family, right? And why we needed an EPIC Energy and say an EPIC Power module. Generally within the electric aviation space, when we're talking about fixed wing aircraft, EPIC Energy will generally meet anyone's need. The missions there are fairly uniform. They're not the same. Obviously, power and energy and whatnot are all different, but the profile is similar. So the way the battery is loaded is very similar. But even if you look at that 10C discharge rate, it actually meets the needs of many eVTOL applications as well. Not all. There's some that need an enormous amount of power, in the order of say 20C or so, which then would put you into the class of say the power module. But the adaptability of that module is of that system is pretty significant. We actually didn't, when we were designing that module, we actually didn't just look at one aircraft or one need or one mission. We looked across the breadth of everything that we had done. We looked at all of the energy requirements that we had seen. We looked at all of the power requirements we had seen. We looked at many voltage ranges that that we'd seen from the different platforms, and we were very key to make sure that we can meet the breadth of that need with this common building block.
Can you help us there? You mentioned C rates there. Can you just help us aerospace journalists, not electrical engineers, to understand really what we're talking about? Because so 10C and 70C, those are discharge rates. 3C is a charging rate, is it? Can you just tell me, and what do you need for the different markets to help us understand?
So maybe Randy, if you want to jump in and talk about the C rate, what does that mean, and really what we're seeing?
Absolutely. So a cell has a certain amount of amp hours in it. I think everybody kind of understands that. So a standard little cylindrical cell might have 3 amp hours. So when we say C, that's a multiplier of the capacity of the cell. That's what the C stands for. So you're discharging a cell at 1C, you're discharging a 3 amp hour cell at 3 amps. If you're charging it at 1C, you're charging it at 3 amps. Most cells have asymmetric charge discharge, meaning you can charge them you have to charge them much slower than you discharge them at. And that's a problem with this kind of, as opposed to automotive where they are trying to go faster. Faster is a relative term. To really hit ROI, our customers are needing really high charge rates. They need to turn the aircraft around, some people less than 10 minutes, some 20 minutes. But obviously that's quite different than the automotive industry, which is looking maybe an hour or 2 hours, and they call that fast charging. When you charge at these higher rates, it does damage a lot of cells. So first of all, a lot of the automotive cells are maybe sub 1,000 cycles, or or less, and then you can't really hit them hard, or you start to reduce that life. So the C rate of charging is important for ROI. Get the asset turned around quickly. It's also critical that you don't exceed a safety threshold. So we're pretty proud that these 3 C rates are very high, and we have done the past couple of years a lot of testing on the cells to confirm this does not impact their cycle life. Right? We get the full cycle life at these higher rates. Discharging for applications is typically much higher, and you may have a need for high power pulsing applications, such as a hybrid, where you may be just kind of supplementing a conventional gas-driven turbine or engine for a short period of time to help boost it. And the reason you might do it, just like a car, right? You're kind of peak shaving. You're trying to keep the engine in a sweet spot so it's more efficient, and you're trying to get some sort of reduction in emissions. And so we do have some customers doing hybrids and micro hybrids. So those are the higher C rates. So when you see the 10C, that's kind of a reason we call it energy, because it is our highest energy cell that we're offering. But it's still, like I said earlier, a lot of people call it a power cell. So 10C for a 3 amp hour cell, for example, will be 30 amps. And the concern there is that if you pull the energy out too fast, the cell will heat up. The other thing that will happen is the voltage will drop. And so although you may be pulling out a lot of current, if your voltage drops, well, that voltage times current is power. And so your power is crippled. So your cell has to be able to sustain these higher C rates. And so we tend to like to have our cells, if it's a 10C cell, or rated at continuously discharge at 10C, this pretty high power for most people, that we can do that without incurring too much heat, and we can do it without the voltage dropping to the point where the electric motors starve for voltage, and it's going to try to pull more current, and you got kind of a problem there. So the cells, when we rate them, these are the viable real-world discharge current rates that the cells can do continuously. The numbers you see on the screen are continuous ratings, 10C, I think the other one's 30C and 70C. They can actually peak for even much higher than that. They can peak for about twice that for a few seconds. Not that we go there often, but it just gives you, these are really high power cells. And they can do so without generating excessive heat in their specific market segments that we're trying to go after with energy, power, and ultra. And they can do without incurring too much internal damage for their cycle life. So they can maintain, and they're highly durable. It can do that for long periods of time. It can do it for month after month after month. And so when we use these C rates, these are realistic numbers. We're not just putting datasheet numbers down that says, hey, it can do that on its best day at high temperature and so forth. These are real world numbers that we believe that we can deploy these batteries into markets to achieve these these long run times that customers need, and get them turned around quickly so that their assets are highly utilized.
If it's helpful, Graham, just as a figure of merit, if you look at a Tesla and you say, what's the fastest that automotive is charging today? It's actually at a half a C. So you can go take your Tesla to the fast charging station. They'll put in 44 kilowatts of load, and it's about an 85 kilowatt hour pack, and it'll take you, a little over an hour or 2 hours to do that. And so when we start to say, well, aircraft actually needs to be at 3C or 4C, that's basically saying I might need, actually, in that same use case of Tesla, somewhere around 160 to even 200 kilowatts of power that's going to be put into these systems. And so you can start to see how this becomes a really big challenge when you're moving that amount of current at that amount of voltage, and you start to do that at scale where we may have 5, 10, or 20 vehicles trying to charge all at once, and it's 4 o'clock in the afternoon in Phoenix. You can start to see where there's going to be some challenges that we have to overcome to make this work.
Can I go back to the launch, the Epic launch? So are all these modules using the same lithium ion cell across all the 3 modules? What are you starting off with in terms of cell type or cell energy density? And is it architected to allow you to move along the the cell type or the cell chemistry as that moves, and how do you see that moving?
Yeah, we have, I guess we've said in the past, and we do say that we are somewhat cell agnostic. The EPIC solution is cell agnostic. Right now, the cell level energy density is roughly 260 watt-hours per kilogram. And then you have the 20% packaging overhead, or less than 20% packaging overhead on top of that. So that's with the current today's chemistry that we have right now. We do have forecasts on improvements to that, and we have the plan in the design of this module to be adaptable to new chemistries or new configurations of chemistries within this module. So the energy density that we would have today would be improved in the next generation of cells, say 2 to 3 years from now, that are coming out, today, and then we have to go through the development process. So we're constantly looking at new cells and new chemistries, and we've designed the module to be adaptable to those.
How do you see that playing out? I mean, do you have an idea of what the next steps will be? Will it be solid electrolyte, or will it be a lithium metal, or will it be lithium salt? Do you know? Have you made a judgment as to how that's going to play out?
Yeah, that's a great question, and it's something that we're looking at very continuously. Maybe I'll make a comment, and then Randy can jump in as well on the chemistry side. We see definitely continued advancement with current, more conventional technologies, and primarily through the adoption of additional anode silicon adoption and anodes and things like that. Advanced chemistries, we've actually worked with a host of advanced chemistry developers and cell providers, and there's some really promising things happening in a number of areas. But big challenges still. As I mentioned before, we're looking at our motivation in cells is obviously safety, cost, weight, and while a lot of these advanced chemistries have great, say, energy density, they may suffer in power, right? Or they may suffer in charging, or they may suffer in cycle life, which then drives the operating cost up. So that we're working with these, we're designing modules with these advanced chemistries. And we're really hopeful for them, and as they come available, and as we show that we can hit the targets in terms of operating costs and efficacy, we'll definitely be in prime position to utilize these.
Thanks, Mike. And Graham, around every corner there's a better mousetrap, and I've been in lithium batteries for 15 years, and honestly, it's only incrementally advanced in that period of time since I've been working with it. It does advance, it does continually advance. There's always the hot chemistry every year, and that's nothing new. And aviation industry is probably more susceptible to a lot of that terminology, just not having gone through the trials of the automotive industry did 15 years ago, which everybody was banking on silicon. Even back in 2008, it was going to revolutionize the automotive industry, and we were going to have 1,000-mile range cars. Well, where are those? They're not here. And automotive is kind of plateaued. I think they're focused on cost now, and so it's packaging density. If you look at lithium metal, it offers smaller batteries. They're not as worried about weight. And their life and their operating just needs to be good enough. 300-mile range, 400-mile range needs to last several years to meet the warranty, and needs to charge fast enough. So they're hitting the point where they're getting what they want, and when they're getting good enough, and it's all about getting the cost driven down so they can undercut conventional automobiles and get their volume up. Aviation continues to strive for higher energy density, faster charging, more cyclability, and is a very different ROI and very different operating metrics. But we are absolutely looking at lithium metal, sulfur, silicon, solid electrolytes. We've been experimenting and testing those the last several years. And so if there's breakthroughs, and as these emerging technologies do come to the front and have value and show that they're viable, then we will be ready for them. We're dealing with how to package them, because it is different than conventional cells. It's a very different things you need to deal with. And so EP Systems has been experimenting with those for the last 3 or 4 years now. And so we would be ready if those technologies, once they're ready to go to market and they've the chemists and the developers have solved all the problems to make them viable products.
So you said at the beginning, you talked about high power and high voltage. What voltages are we talking about with this initial EPIC family of modules?
So the modules are designed to be individually relatively low voltage. And the reason for that is because we understand people will be touching these and handling these. So we like to have non-high voltage, fairly mechanically manageable products that people can lift, put, move, take out, deal with, that aren't 500 volts. So they're all under 100 volts, and most of them are under the 60, 50, 40 volt range. They're configurable, so I can't give you one answer, because inside the modules we can reconfigure the cells in parallel and series to meet different objectives without changing the case structure. They can be put into series in the system up to high voltage. We've done up to 800 volts. There's discussions up to 1200 volts. Obviously, higher voltages provide a lot of value by reducing current for the same power. So customers who are doing over 1 megawatt of power really want high voltage, because otherwise to get that power level, your current goes high, which means you have to have heavier cables. You'll have more losses typically in your cables if you don't have heavier cables. So it's kind of a weight efficiency play. Problem is 1200 volts, it's kind of a new thing. High altitude, getting over 30,000 feet at 1200 volts, it seems to be very untrodden territory. And so there's connector issues, there's arc corona effects, there's other things that we have to deal with that we're looking at. There are applications that we're working on that are going to be over 35,000 feet and high voltage. But for most of our customers, it's a lower altitude and sub 800 volts. A lot of them in the 600 volt range, some 500. So we can deal with things like 250, 300, 400, 500, 600, 800 volts all day long. That's generally not a problem. Most customers aren't going below about 300 volts because obviously the numbers don't work for the power we're talking about for any application. So they can be put in series to get to the voltage that people need, and our supporting systems such as disconnects and so forth, cables and connectors support those higher voltages.
Right. So somebody just popped up with a question I was about to ask, and that is, so the module includes the provisions for liquid cooling, but do you include the mass of the liquid cooling system in your overhead, or does that get booked to the airframe as being a weight?
Mike, you better address that question.
Yeah, I can jump on there. Right now, as the mass overhead right now does not include the external the cooling system, and there's a couple of reasons for that. One reason is that the cooling system is in some cases it's not even necessary on board the aircraft, as long as the modules are preconditioned and you're operating in a pretty standard flight condition, or any potential flight condition for a fixed wing application. There's no cooling required. Even some eVTOL missions, there wouldn't be necessarily active cooling required as long as the module is preconditioned during charge. And so that's why we don't include that overhead mass in the module weight, because it really is platform dependent. In some cases, it buys its way on. In some cases, it's entirely necessary. And in other cases, we rely on preconditioning.
So as a business model, is it EP Systems' intention to sell the battery system? What happens in the second life? Do you then get sort of like, do I come in and like my used PT6, do I come and trade my battery modules back to you so that you can put them into a secondary application? And then do I trade them back again to say that you dispose of them? And what's the actual sort of the approach there from the business model?
Yeah, I think Nate could probably jump in there. That's a really good question.
Yeah, so we have a whole thought around that. Secondary life is a big question, and secondary life has huge advantages if you can make it work. And there's been a number of people have looked at it. There's some major technological hurdles to secondary life and reuse, and what most people don't understand is when things come off an aircraft, they're all going to be in different states. And so one may have degraded by 30%, one may have degraded by 50%. And when you typically build batteries, you match them very, very closely, and you manage the environment so that they wear uniformly. You also put balancing circuitry around them to ensure that they're going to wear evenly. And when you start to say, hey, I might just take something off the airplane and I'm just going to plug it in right here, it's like, well, normally when you get to a grid asset, or you get to a secondary life asset such as a grid asset that can use it, it's a big, big integration problem. We're really interested in this space, and we've been working on some advanced technologies, mostly on the control space, that overcome that mismatch issue. So we do intend to make an announcement on how that's going to work. We are very, very interested in services. We are very, very interested in secondary life, and we hope to make some announcements and actually do some demonstration on how our vision would be. That
So I think we're breaking up a little bit there, Nate. So thanks very much. We're kind of wrapping up here. Can we just ask, are you guys still, I mean, you got your start with X57 and you learned a lot of hard lessons with X57. Are you still involved with X57 program? Or?
Yes, we are. So we still engage with X57 as an ongoing program that's getting pretty close to hitting some key milestones this year that we're really excited to see that initial Gen 1 system fly. So we still engage with them. X57 has also proven to be a very, very valuable program in maturing some of the certification thought process and what the framework will be in the future. And we still see those opportunities to engage with NASA and other regulators to use that as a test bed to mature our cert frameworks.
You certainly seem to learn a lot of your early lessons on that program. It gave you a good start on your pathway to safe and certifiable design approach. So. Good. Okay. Well, I think we're getting to the end of our hour here. So, guys, do you have any thoughts to wind up before we hand back to Jim? Anybody?
I think I always want to express gratitude, Jim, to you and Graham, and to everybody who's taken part. We really appreciate it and have very much enjoyed the time here.
Well, I want to thank you guys for giving us such great insight into a company that a lot of us have been aware of, and we've been wanting to know more about you, but and you've been able to do that for us. So thank you to you, and thank you to VFS as always for being the enabler. Back to you, Jim.
Thank you, Graham, and thank you, Nate and Randy and Michael. This was fantastic. We are really excited about these new modules. And Graham, wonderful job as always with moderating the final part of the session. We'll get this recording posted as soon as we can. And I do want to query Nate, Randy, and Michael, if I pull the questions, because there were a few that we didn't quite get to today. If I pull those and send them to you, would you mind providing a written answer that we can post along with the video for people to address?
Yeah, there were a couple of really deeply technical ones that A, I didn't understand the question, and B, I'm not sure we could have got an answer in anything shorter than half an hour. So.
Yes, there are a couple of those, but yeah. So
yeah, we can take a look at those.
All right, that'd be terrific. Okay, so with that, we will wrap up our eVTOL Writers Group interview for today and look forward to scheduling our next one. We also, I just want to let you know that we have the eVTOL short course coming up next week. And that's a 2-day course taught by Professor Madhubab Datta with Michael Ricci from LaunchPoint, Bob Hess from BAE Systems, and James Bader from the University of Maryland. This will be I think it's our 5th eVTOL short course, and there's a lot of extra material in this time. And then we'll have another short course coming up the week after on cost estimating, as well as the FAA Vision Systems Summit. And then we have an eVTOL Flight Test Council meeting on eVTOL certification coming up after that. So if you check out vtol.org/webinars. You will see all the upcoming programs for at least this month, and then we have a few things coming up later in the year as well. So look forward to seeing you online down the road, and we'll sign out from here. Again, thanks to our friends at EP Systems and to Graham for another great session.